Good afternoon, all you calculus fans out there. So today's topic of this video is going to be Riemann sums with graphs. So the entire idea of a Riemann sum is that it is a method used to find the area underneath a specific curve. Now, with Riemann sums, there are three different types that you can use. There is the left Riemann sum, the right Riemann sum, and the trapezoidal Riemann sum. Each are a little bit different. So, to begin with, the left Riemann sum, when using points on the graph, creates intervals starting from the left. So, as you can see from what she is doing, she is taking the point from the left, bringing it across the interval, and then dropping it down to create the entire space underneath the curve. However, if the graph is increasing such like that, using a left Riemann sum can create an underestimate, where there is negative space below the curve that is not accounted for. Though, if the graph is decreasing, then it creates extra space above the graph, creating an overestimate. So, that means no matter which way the graph is going, whether it's increasing or decreasing, there will be some variance. So now, contrarily, the right Riemann sum starts from the right point and drags an interval left from that specific point on the graph. So, as you can see now, she is taking a point on the graph, dragging an interval left, and creating a space underneath the curve. So now, if the function is increasing with the right Riemann sum, there will be an overestimate. But then if the function is decreasing, there will be an underestimate since there is the negative space underneath the curve. So, just like the left Riemann sum, the right Riemann sum creates some variance, just in the opposite direction, where the left would be an over and then the right an under. The example problem we chose to use was the equation y equals x to properly show how an overestimate and an underestimate are different. To find a left Riemann sum, it is just the combined areas of all the rectangles that are created, and an area of just one of those rectangles is the height of that left point multiplied by the subinterval length. So, our first area is just going to be the height, in this case it is 0, multiplied by the subinterval length, which in this case is 1. So 0 multiplied by 1 is just going to be 0. And that is going to be our first, although non-existent, rectangle in our left Riemann sum. Now, the next rectangle will be an area of 1 since it is 1 unit high and consistent with our 1 unit subinterval length. Fast forwarding through multiplying the remaining heights and subsequent interval lengths gives us a Riemann sum of 10 units squared, although with some negative space underneath the curve, creating an underestimate. Even though this is an easy equation, in a real-world setting you can account for that extra area without taking the integral itself, though shrinking the subinterval length can help eliminate some of that error. Contrasting the left Riemann sum, the right Riemann sum uses the same method of finding the areas of the rectangles underneath the curve and summing those areas. The right sum now uses the point on the right as the height instead of the point on the left. For the purposes of our example, we'll keep the subinterval length the same, which is just 1 unit. Now, the height of the first rectangle will be 1, multiplied by the subinterval length of 1 creates an area of 1 for the first rectangle. Following with the second height being 2, keeping the subinterval will create an area of 2 for that second rectangle. Once again, fast forwarding gives us a total sum of 15 units squared for the equation y equals x from 0 to 5. Now, with the same equation y equals x, a right Riemann sum gives us an overestimate since there is extra space above the curve. This next sum is going to be a little bit different. It's called the trapezoidal Riemann sum and connects each subinterval point on the graph with a straight line from point to point. As she connects the lines, you'll be able to see trapezoids form underneath each line. With an increasing function, the trapezoidal sum creates an overestimate, and with a decreasing function, it creates an underestimate of the curve. Though, it should be noted that this is the most accurate sum. For our example equation, we used y equals x cubed plus 4 to keep it above the x-axis and to demonstrate an over and underestimate in one graph. With our straight lines connected, we can solve a trapezoidal sum, which is just summing all the areas of the trapezoids formed from those connected lines. To find the area of the trapezoid, it is simply the height of one, in this case beginning point, added to the second point, then that sum divided by 2 to find the average height. That is then multiplied by the distance between the 2 points, which we know as the subinterval length. So our first trapezoid, starting at y equals -1, is going to have its first height be 3, and our second height will be 4. Those two added are 7, then divided by 2 is 3.5. Multiplied by our length of 1 will give us an area of 3.5 for our first trapezoid. Solve the rest from -1 to 2, and that gives us an area of 16.5 units squared under the curve. The left part of the equation is decreasing, creating an underestimate from the sum, and the right part will give us an overestimate. That variance happens because the trapezoids account for linear change, whereas the graph is not linearly changing. On to our challenge problem. We will be doing all three Riemann sums of the function f equals sine pi x plus the sine of 4 pi x over 3 plus 3, and our intervals will be at every maximum and minimum on the graph from 0 to 5.58. Starting with the left Riemann sum, our first height will be 3 multiplied by the interval length of 0.42, giving us a first area of 1.26. Now done with the busy work of working through all the math and finishing up our final interval, we arrive with a total area of a left Riemann sum of 18.2 units squared. For a comparison later, we'll drop that 18.2 units squared down at the bottom. So now that I have time, and she won't see this, I want to say thanks to Miranda, as she's drawing all of this craziness and I just talk over it, so thank you. So moving right along into the right Riemann sum, we do the exact same thing as the left, except starting from the right point. Our first height is going to be 4.95 and an interval length of 0.42 again, giving us a first area of 2.08. Moving right along into our final area of 0.88 and summing the previous areas gives us a total area under the curve of 15.78 units squared. Once again, putting that value at the bottom for later comparison. Once again, thank you Miranda for redrawing and rewriting all of this and going along with my crazy equation. The last Riemann sum will be the trapezoidal sum, and just like before, it'll be the first and second height added, then divided by 2 to find the average height. Then that value multiplied by the interval length to give us the area of the first trapezoid, which in this case is 1.67. With the last interval solved, we sum the trapezoids to find that the whole sum of it equates to about 16.95 units squared. Now, for the complete summary of our data. Since we have our three values, Let's see how that compares to the value of the integral of the equation, aka the real area under the curve. The value of the integral equates to about 17.26 units squared. Compare that to the left sum value of 18.2 and we get a difference value of around 0.94 units squared. The right sum value is 15.78 and gives us a difference of about negative 1.48 units squared. The trapezoidal sum value is 16.95 and has a difference of negative 0.31 units squared. The left Riemann sum is an overestimate, the right Riemann sum is an underestimate because it is negative, and that means that the trapezoidal sum is also an underestimate of the graph. Disregarding the negatives and solely looking for the smallest difference, we can clearly see that the trapezoidal Riemann sum was by far the closest. Just like we had said before, that sum has the highest accuracy. Thank you for watching our video, and we hope that you understand Riemann sums with graphing just a little bit more.